Application of Haar Wavelet Discretization method for free vibration analysis of rectangular plate. Abstract. This paper focuses on the Haar Wavelet Discretization method, HWDM, for solving the problem of free vibration behavior of rectangular plate. The displacements are expressed as Haar Wavelet series and their integral. Since the constants generated during the integration process are decided as the setting of boundary conditions, therefore, the equations of motion of the entire system including boundary conditions are expressed as a series of algebraic equations. By solving the eigenvalue problem of these algebraic equation, the natural frequencies of the rectangular plate can be obtained. The accuracy and convergence of HWDM is verified against the results of the previous data, and the comparison results agree well. The effects of several geometric dimensions on the natural frequencies of rectangular plate under various boundary conditions are investigated. The numerical results for rectangular plate obtained by Haar Wavelet Discretization method may be served as benchmark solutions for future research. Keywords: rectangular plate, Haar Wavelet Discretization method, free vibration, numerical analysis, eigenvalue problem. Introduction. Plates are widely used in various engineering fields, and especially, in the case of ship and ocean structures, they can be considered as one of the fundamental structural elements. It is very important to investigate the vibration behavior of plates which are widely used in various engineering fields. A lot of scholars have published a number of papers on the free vibration of rectangular plates 1 to 13. Different methods such as Rayleigh-Ritz method, Galerkin method, finite element method and the method of separation of variables have been used to analyze the free vibration of rectangular plate. The results of the review show that although many studies have been conducted to analyze the free vibrations of rectangular plates, finding a reasonable approach to obtain the natural frequencies of rectangular plates is still an important problem. The Haar Wavelet Discretization method is a very simple and powerful method to solve the eigenvalue problem, and the application in engineering of this method will be reviewed below. In 1909, A. Haar proposed the Haar function, which made a great contribution to the emergence of wavelet theory. In 1981, J. Morlet 14 proposed the wavelet concept, which laid a good foundation for the formation of wavelet theory. Since then, the research of wavelet theory has entered a stage of rapid development. In 1981, Stromberg improved on the basis of the Haar function and found the first orthogonal wavelet. In 1982, expert Mar formed the Mexican hat wavelet. In 1985, Meyer obtained a smooth wavelet orthonormal basis with a certain attenuation, namely Meyer base 15, which laid a good foundation for the further development of wavelet theory. In 1988, wavelet analyst Dobes 17 constructed an iterative method to construct a wavelet base that is non-zero only in a finite region, i.e. Dobes base, and gave 10 presentations at a wavelet conference held in the United States. It caused a sensation, and then the book Small Waves 10 became a great book with great influence in contemporary mathematics, which pushed the development and practical application of wavelet theory to a climax. In 1989, Mallet 19 proposed the famous Mallet algorithm, which opened the development space for the engineering application of wavelet theory. After the 1990s, wavelet theory gradually matured. At present, research on wavelet theory has penetrated a wide variety of fields. Majak et al. 2021 developed Haar wavelet-based discretization method for solving differential equations, discussed both strong and weak formulations-based algebraics, and introduced this method to solve solid mechanics problems. Recently, Hein and Feklistova 2023 applied HWDM for solving the vibration problems of functionally graded beams under some boundary conditions. As can be seen from the literature review, the Haar method was used for vibration analysis of various types of structures, but two-dimensional development is difficult, so there are very few examples applied to the vibration of plate structures. Therefore, the main purpose of this paper is to establish a solution method and system to apply conveniently and efficiently the Haar Wavelet Discretization method to the free vibration of a rectangular plate. 2. Application of HWDM. Haar wavelet, which is a group of square waves that has size of +1 and -1 in some intervals and has zeros in elsewhere, is one of the simplest compactly supported orthogonal wavelet among the wavelet families. The details of Haar wavelet series and their integrals can be found in the following references 25 to 28. HWDM are used to discretize the derivatives in entire governing equations including boundary conditions. Since the Haar wavelet series is defined in the interval 0, 1, firstly, in order to apply the HWDM, a linear transformation statute may be introduced for coordinate conversion from length interval 0, L of the rectangular plate to the interval 0, 1 of the Haar wavelet series, that is. In the HWDM, highest order derivatives of the displacements are expressed by Haar Wavelet series, the lower order derivatives can be obtained by integrating Haar Wavelet series. The transverse vibration differential equation of the plate is expressed as, where d is the flexural stiffness of the plate, is defined as 42 HKD equals 321/121 de equals. Substituting equation 2 into equation 1, the vibration equation of the plate at local coordinates is defined as, by taking n equals 2m, f, dot, equals w, dot. When is fixed, w is a function containing only the variable, and the highest order derivative can be approximated by Haar wavelet along parallel to the axis. By integrating the EQ, 4, the following derivative terms can be obtained. The displacement function v, dot, can be written in the form of a matrix as following. In practical process applications, the clamp boundary condition, simply supported boundary condition and the free boundary condition are widely used. These boundary conditions can be written as follows in equation form. Clamp boundary condition. 4 boundary condition equations can be obtained by introducing the boundary condition, and can be written as follows in matrix form. Considering the boundary conditions, it is easy to know that f is a zero vector with a length equal to 2n, and it will be omitted. E is the unit matrix. Similarly, the following expression will be used to calculate the Haar wavelet expression of the fourth order mixed partial derivative of w. If g, dot, equals 0.2 w/2, the second derivative of g, dot, along the parallel axis, can be approximated by Haar wavelet. By integrating second derivative of k in turn, the following expressions can be obtained. 2 boundary condition equations can be obtained by introducing the boundary condition, and can be written as follows in matrix form. In this example the boundary condition is set simply supported boundary condition, in simply supported boundary condition g, dot, equals 0.2 w/2 equals 0, dot equals 0, equals 1. By combining EQ, 18, and EQ, 19, the following equation can be obtained. From EQ, 20, an unknown coefficient matrix is defined as. Therefore, the second order derivative of displacement g can be expanded into the following as, where n1 and n2 are the first n columns and the last 2 columns of the matrix. 122 HQ. Similarly, for k, dot, equals w, dot. By combining EQ, 23, and EQ, 24, the following equation can be obtained. Therefore, the second order derivative of displacement I can be expanded into the following as, where t1 and t2 are the first n columns and the last 2 columns of the matrix. 133 HQ. From above equations, we can obtain as following expression. Therefore, a governing equation for an orthogonal isotropic plate expressed by Haar wavelet and its integral can be obtained as. Therefore, the natural frequency of the plate can be easily obtained according to equation 28. 3 numerical results. In this section, new numerical data that future researchers can use as benchmarks are presented along with parameter studies. Table 1 lists the first 4 order natural frequency parameters of square thin plates with constant thickness under different boundary conditions using Haar wavelet, where Lx equals Li equals 1m, H equals 0.1 m and material is steel, E equals 210 GPa, equals 0.3, equals 7800 kg/m3. It can be seen that a small number of matching points can achieve good numerical accuracy, and with the increase of the scaling factor j, the numerical results are getting closer and closer to the literature 24, thus proving that the structure is solved discretely using Haar wavelets in both directions. The natural frequency is feasible, and the boundary conditions can be accurately applied, which proves the feasibility of the method and provides a basis for the use of this method in more complex structures. Table 2-5 shows the natural frequencies of the plates for different thicknesses under several boundary conditions using presented method. Fig 1 shows the natural frequency change of the plate with increasing A under several boundary conditions. As shown in the Fig. 1, the natural frequencies are decreased as Li/Lx increases. In particular, it can be seen that the natural frequencies are decreased rapidly until Li/Lx equals 1, then are gradually decreased. Lastly, Fig 2 shows the change in natural frequency of a plate with a completely clamped boundary with increasing thickness h. It can be clearly seen from the figure that as the thickness h of the plate increases, the natural frequency also increases. 4 numerical results. In this paper, a reasonable analysis method based on the Haar wavelet has been presented to obtain the natural frequencies of rectangular plate with several boundary conditions. The basic principles and formulas of the Haar wavelet collocation method are described, and its approximation to displacement functions using HWDM are discussed in depth. The solution process of Haar wavelet used in free vibration analysis of rectangular plate is given in detail. The efficiency and accuracy of presented method are proved for natural frequencies of rectangular plate with several boundary conditions. Some conclusions obtained through numerical examples and free vibration analysis results for the rectangular plate are presented. These data may be served as benchmark solutions for future research. Acknowledgement. The authors also gratefully acknowledge the supports from Pyongyang University of Mechanical Engineering of DPRK.